let's go for it here. So chapter 3, we're on 3.4. And so if we sort of give a quick review of stuff, 3.1 was all about quadratics. How do we find zeros? We can factor them down. Now we find zeros in a quadratic equation here. We have also the whole concept of decreasing and increasing, right? With parabolas, you have a section where it's increasing, you have a section where it's decreasing. We talk about intervals in that time. 3.2 was all about polynomials. So in this case, again, you're still trying to find zeros, still trying to find everything else with it, but now you have yourself a degree 4, maybe degree 5 polynomial. And last time, 3.3, we talked about the whole concept of how do we find, not how do we find zeros, but we learned about synthetic division, is that right? We learned about long division, and we learned about the factor theorem, but most importantly, as we just did off the homework, we learned that if you have a remainder of 0, that means you have a factor. That means that thing divides evenly into the other, or that divisor divides evenly into the polynomial. We're going to use that because the whole game of 3.4 is to find your zeros. And there's a whole bunch of stuff here. I'm not going to actually do all of them. Descartes' rule of signs we're not going to do because it's really not that useful. I haven't really seen it later on. Sometimes in theoretical mathematics it comes up, but that's about it. So let's go for it here. So whole concept here is really just find the real zeros of a polynomial. We're going to look at the rational zeros, and then we're also not going to do the bounds. We can skip that as well. But really what we want to do is this last part right here. We're going to try to figure out a procedure for finding all the real zeros of a polynomial function. How do you find all the x-intercepts, technically? That's what we want. We looked at in behavior last time. Did we look at in behavior? Sometimes it starts high and ends high. Sometimes it starts low and ends low. All that stuff we're going to sort of put together finally into one complete package. So let's go for it. How do we find all the zeros? Well, we have a little rule here. Let me back up just one here. It's called the rational roots theorem or rational zeros theorem, depending on which book you're using here. So kind of looks weird at first, a whole bunch of variables and numbers here, but if we describe a polynomial, any polynomial, you have coefficient in front and x to the nth power. Again, could be 5, could be 10, could be 28, whatever it is. And you just sort of keep on going down all the way down to x to the second, x to the first, and then there's your constant term all the way at the end. We good? Here's what we got. We have this thing called P over Q. And this polynomial has rational numbers or rational roots. And if it does, it's all the factors of, and again this little p here is all the factors of a sub 0. All the factors of your constant term. Q is all the factors of your leading term. Kind of fun at first if you sort of think about it. Like, wow, we can actually find any polynomial, any zero polynomial, zero of any polynomial, just because of those two numbers there. Just, I think it's kind of cool, the fact that we can do that. Let's look at an example first, and then we'll practice one here. So it says find all the rational zeros of this function here. Again, maybe don't need to write it down unless you really want to here, but let's think about it here. The p-value is all the possible factors of your term all the way at the end, or the constant term. So think about all the factors of -3. Well, you got, let's see, 1 and 3, right? And all the different combinations, because you could have a negative and a positive, or a positive and a negative. So all the factors of -3 are plus or minus 1, plus or minus 3. Then we look over here, the Q value. The Q value is all the factors of the leading coefficients. All the different ways you can multiply to get 2. Let's see. 1 times 2? Or -1 times -2. So you got all these possibilities of plus or minus 1, plus or minus 2. And then what you do is you really just divide these two terms against each other here. So 1 divided by 1 is this 1 plus or minus 1 here. 1 divided by 2 gets you that plus or minus 1/2. 3 divided by 2 gets you a 3/2. And then again, also 3 being divided by 1. So all the different possible combinations for division. So here's what we're saying. This polynomial has roots or x-intercepts, and if there are possibilities of any one of these 8 answers right here. And if they're not any one of those 8 answers, then we really got either a square root kind of square root answer, or we got ourselves a irrational answer. Irrational answer or a complex answer. Like, remember that square root of -3 or something. But if it's fractions and if it's integers, these are the only possible values they could possibly be. Cool. All right, so let's go for it. Let's do one together here. So I need find all rational zeros of f of x. And again, we're sort of slowly putting everything together here. Some of these problems will take a little bit of a long time. So P is all the factors of the number all the way in the back. So how about all the factors of 8? Plus or minus 1. How about plus or minus 2, plus or minus 4, and plus or minus 8? Are we good there? Let me go over here. The Q value. And again, some math books, they use a capital Q, some use a lowercase q. Some use a capital P, some use a lowercase p. It doesn't matter. I prefer the uppercase because it sort of stands out a little bit more. Okay, all the different ways I can get, or factors of 2's, plus or minus 1, plus or minus 2. Okay, so here it is. All the different possible rational zeros is P over Q. So I got to divide one to the other. The easiest way to divide in my mind is, first of all, I take this little 1 for Q, and if I divide all the P's by 1, I'm still going to have the same thing, right? So 1 divided by 1 is still a 1. 2 divided by 1 is still a plus or minus 2. 4 divided by 1 is plus or minus 4. And again, 8 divided by 1 is plus or minus 8. In my mind, that seems to be the easiest. And then we just start dividing by 2. So let's see. Now, 1 divided by 2, that'd be a plus or minus 1/2. Everybody good there? Going back here. So 2 divided by 2, that would be actually a 1. We already have that one, so we don't need to write it down again. 2 divided by 2 is a 1. We already have it. 4 divided by 2 is a 2. We already have that. And then 8 divided by 2 is a 4. And I already have that. So there it is. 1, 2, 3, 4, 5. I got 10 different possibilities for my rational zeros. Again, what we think about rational is fractions or integers, whole numbers, stuff like that. So now the question is, how do we figure out which one's the rational zero and which one is not? You got to test them. So you got one of 2 ways to do it. You can either use synthetic division, but an easier, let's use the remainder theorem. Let's do this. So let's just pick one of these here, plug it in for f of whatever it is, and we're going to work it until we get 0 as an end result. Which kind of makes sense, right? If you say, I'm going to plug in, let's just say I'm going to plug in 1/2, right? If I plug in 1/2 and I put it in here, I do all that work and I get a 0, doesn't that mean it's actually on the x-axis? If my y value turns out to be 0, if my f of 1/2 value. Okay, so you guys tell me here. Let's try it. Let's thank you. Let's do this here. How about one side of the room here? You guys do +1. We're good? +1. Plug it in remainder theorem, see what happens. You guys do -1. Fireball, the left side of the room where David is. David, you guys do a +2. So the left side of the room, yeah. And then the right side of the room, you guys do a -2, just to see what happens. Plug it in, just put f of 1 or f of -1. Just see if we get a 0 out of it. You guys, yeah, you guys are plugging. Don't do synthetic division yet, because it'll be a longer time to do so, as opposed to just plugging in values. So, the Kalinga room, that's my side, you guys are going to plug in a +1. The other side of Kalinga plugs in a -1. Alright, David's side of the fireball plugs in a +2, is that right? Other side plugs in a -2. You guys tell me if you get a 0. Okay. My side in Kalinga says +1 does not work. Is that right? Okay, cool. -1, did it work? No. Okay. Fireball, +2, did that work? They had a harder number to plug in, that's all. Let's go wait a little bit here. No answer yet? Tell me when you get it. Oh, the other side, how about a -2? Did -2 work? Yes or no?
Yeah.
Oh, okay, got it. -2 worked. Awesome, okay, let's go with -2. Since -2 worked as far as plugging in stuff, we just figured out that -2 is an x-intercept. Now we're going to use synthetic division. So the synthetic division here, -2 as a number inside the half square here. So we're going to bring down the coefficients here. How about a 2? How about a 3? -6 and -8. And again, we're going to check it here. And we should be able to get a 0, right? If we don't get a 0, that means we did something wrong. Yep, I see people saying yes, we got a 0, so 2 goes down. -2 times 2 is -4. Adding those up gives you -1. Multiplying by 2 gives you a 2. Then adding down gives you -4. Multiplying -2 gives you 8, and voila. Okay, can you write for me the polynomial that's left over? So again, we talked about it last time here, you can go one of two ways here. If you know you start off with x to the third, you know now you have x squared, right?
So 2x squared x minus 4.
Awesome, cool. 2x squared minus x minus 4. So it's coefficient of x squared, coefficient of x, and the constant coefficient. Next, we're going to take a look at this guy. And the question is, does this guy reduce? Now, once we get down to x squared, we're not going to do p over q, because we have two legitimate ways of finding. We can either factor, if we can. And if we can't, we always have what works all the time? Quadratic formula, right? That works all the time. So let me rewrite this. And the first question is, can you factor that easily? Got it, okay. Got a couple of people saying no, Mr. H, you can't do that easily. Thinking to myself here, no, can't do that easily. Okay, so if I can't factor, then you might as well plug it into the quadratic formula. Alright, so let's go with it. Hopefully you guys remember the quadratic formula from a long time ago here. It's opposite b plus or minus b squared minus 4 times a times c. And then at this point, my radical is not long enough, so I'm going to extend it out a little bit further. On the bottom, it's 2 times a. So again, math 15, folks. You should have that memorized by now. Alright, simplifying that as much as we can. Let's see, 1, that's going to be 1 squared. Yeah, plus 32, I guess, right? So 33. over 4? Yep, there was no way we could have factored that one down. So no way. Okay. But we got it. The only thing is, we know that this is not a rational 0. Is that right? It is a 0. It does cross the x-intercept. But the directions for now, for practice problem number 1, is find all the rational zeros. Eventually we'll get to find all the zeros. Cool. But since this is not factored down anymore, this is not a perfect square. This case, this is not a rational root. So the only rational root is that -2 that we found initially. All right, we're good. So we're really just finding not all the zeros, just finding the rational zeros. That's the whole game here. Okay, so let's go on to the next one then. Next one is now find all the zeros. Practice problem number 2. I'll just solve this equation. So now at this point, yes, you do want to solve for the irrational, the square roots, if you can. Very similar to number 1. Let you guys try it yourself here. Yeah, and give you guys a head start, just for a little bit. All right, trying this together. Those who are waiting for me, here we go. P. P is all the factors of your constant term. So in this case, it's that little -1. So plus or minus 1. Go then with Q. Q is all the factors of your leading term. So in this case, you got this little 2. So how about plus or minus 1 and plus or minus 2? Okay, then all yours here. Can you list for me all the possible rational zeros? P over Q, or P divided by Q. Let's see. So P divided by Q, if we're going to do it this way, it's going to be, again, 1 divided by 1, which is plus or minus 1. Then we got 1 divided by 2, in this case, plus or minus 1/2. Cool. So 4 different possibilities here. That's all we got. All right, here we go again. Let's go with, if you haven't found it yet, or some may have found it already. Plug in a 1 into that, see if you get a 0 is equal to 0. Plug in a -1, 0 equals 0, yes or no? Then this tough part, of course, plug in a positive 1/2 or a negative 1/2. Whew, have fun. How about this here? Those in Kalinga, can you guys plug in a positive 1/2? Those in Fireball, plug in a negative 1/2. We'll see which one gives us the 0. I don't think 1 works. 1 would not work here because you get a 7, you get 3, and no, it's not going to work. 1 is pretty easy to tell. You're going to get yourself a -2 with a positive 1. Then you're really off with a -1 at that point. Start adding them together here. So you got 8, 17, 18. You get -18 if you add a -1 in there. All right, Kalinga people, positive 1/2. Fireball people, -1/2. Tell me which one gives you the 0. Okay, we got an answer here in Kalinga. We're saying yes, a positive 1/2 works. Cool. Again, we need to find one of them, and that's the thing. When you're doing your homework by yourself, not so fun because you got to test all of them. So in Kalinga, we found out that the positive 1/2 actually works. Once you know the positive 1/2 works because you plugged it in, now let's do synthetic division on that 1/2. All right, the coefficients here of x to the third is a 2. Coefficients of x squared, negative 9. And then the coefficient of x is 6. And your constant coefficient at the end. Setting it up for synthetic division. And again, we should get that little 0. It'll confirm that this is, in fact, a factor. Interesting. We got a fraction. I think this is the same first time we did a fraction with synthetic division here. So 2 plus nothing is 2. And then in the multiplier here, 1/2 times 2 gives you just a 1 right here. Negative 9 plus 1 is a negative 8. Okay, hey, that's working out. This is good. Half of negative 8 is negative 4. Hey, this is actually working out nice. 6 subtract 4 is a 2. Then again, half of 2 gets you over here to a 1, and voila. Awesome, like that. Normally what happens, since we are solving an equation, what we do is we want to write sort of like the factored polynomial. Keep on going, just like you did in algebra. So here's what I'm going to do. Since I know 1/2 is a factor, see if you guys agree here. X minus 1/2 is the factor that I got from here. Cool. Does that make sense there? It's what causes the 0. The 1/2 is the thing that causes the 0 here. So x minus 1/2. Then what I do is I take, again, 2 goes down because that's the coefficient of x squared. That's the coefficient of x. Positive 2 is the coefficient, constant coefficient equal to 0. There it is. There's my factored polynomial. That's cool. I'll say this a whole bunch of times here. Once you get down to x squared, factor or quadratic formula. That's all we got. All right, let me rewrite it because I'm running out of room here. Let me just write this exact same thing over here. So x minus 1/2. There it is. This one's easy to take care of. Got that. Our concentration now is this right here. So 2x squared minus 8x plus 2. You know, can we factor out a 2 here? Yeah, let's factor out a 2. Gives us x squared minus 4x plus 1. Good there? They're just kind of solving as far as we go here. Can I get rid of the 2, right? Technically, I'm going to divide both sides by 2. But what I get to do is I just get rid of the 2 there. Divided both sides by 2. Can I factor x squared minus 4x plus 1? Okay, people shaking their heads no. Okay, then I'm left with the quadratic formula. Opposite of b, plus or minus b squared, which is 16, minus 4 times a times c, all over 2 times a. All right, if I do that, let's see, 4 times 1 times 1 is 4. So how about 4 plus or minus the square root of 12 divided by 2? All right, so let's see. 12 is actually 4 times 3. In that case, 4 on the outside. Let's see, that means 4 times 3, square root of 4 is 2, so 2 root 3 over 2. And then we reduce that as much as possible. So again, the 2 has to reduce this number here, and the 2 reduces this number at the same time. 4 divided by 2 is a 2. And then 2 and 2 reduce completely, so we're just left with a root 3. All right, can you write for me all 3 solutions? Can you say x equals and give me the answers? There's 3 of them, or there are 3 of them. All right, hopefully you guys got it here. So don't forget the x minus 1/2 right here. That's a 0 at 1/2, comma, and then we bring in this right here. And the book, sometimes what it does, it'll write it like this. Sometimes it'll write it as x plus root 3, comma, x minus root 3. Just know there's 3 answers there. Okay, we're good there. So far, we've been starting off with x to the third power, right? We get x to the third, we do p over q, we get it down to x squared, and we got ourselves quadratic formula factoring. Let's step it up one more. Let's start off with x to the fourth first. So what should we do then? We're going to have to do p over q twice, right? We're going to start off with x to the fourth. We're going to do p over q to get it down to x cubed. But then since we're in x cubed, we're going to have to do p over q again to get it down to x squared. We got so one more extra layer on top of it. So I'll let you guys try it. Oh, before we do that, sorry, I should mention this. There's something called the Descartes Rule of Signs. And Descartes, brilliant mathematician and philosopher, he figured out a way to, because you have plus or minus 3, plus or minus 7, plus or minus 12, right? These things can get humongous with more factors. So he figured out a way to tell which ones you can sort of cut off immediately from those rational possible zeros. Sometimes it works good, sometimes not so good. We usually don't use it in higher mathematics. It's not sort of that important. Also, there's another one. It's called the rules for bounds. So x has to be between this number and this number. Same exact concept. You're sort of limiting your possible p over q values. But at the same time, doesn't do that good of a job. And again, not used because you can just test different possibilities for p over q. Okay, so let's try this one then. Starting off with a 4th degree polynomial. Oof, okay, I'll let you guys get started just a little bit. And those waiting for me will start in just a bit. But try it yourself first. We have already 2 practice runs with this. Alright, those of you waiting for me, let's go for it. So, I got to find a p over q. So first p is all the factors of 12. That's going to be a long list. Not so fun. Let's go for it. All the factors of 12. So plus or minus 1. Let's see, 2 would do it. 3 does it as well. That's right, 3. 4. Wow. And 12. Gee whiz. Okay. Okay, let's go with q then. All the factors of 3. Okay, this one's at least a short list here. It's 1 and 3. That's it. All right, p over q. So again, all the divisors that could possibly happen. Again, assuming q is equal to 1, as you divide each one of these here, you're going to get 1. You're going to get exactly the p values again. 2. You got 3. You got 4. Again, this is assuming that q is equal to 1 right now. 6 and 12. Go back over here again. Okay, now we're going to take that divisor of 3 now. So now we go 1 divided by 3, plus or minus 1/3. 2 divided by 3 gets you 2/3. 3 divided by 3, hey, that's cool. I already got that. That's 1. Let's see, 4 divided by 3. Oh boy, that's okay. You got 4 divided by 3. 6 divided by 3 is the 2. I already have that. 12 divided by 3 again gives you a integer value, and we already have the integer value of 4. All right, not too fun. But has anybody found a 0 yet? No happy faces in the audience. Nope. Okay. Few little hints of the trade. We good? Notice you have a little 3 in front over here. Whenever you factor things, and think about factoring here, this would finally reduce down to maybe like a 3x plus something, right? And a x plus something. So one of these divisors of 3 is going to work because of that 3 in front. Good there? You sort of know that, and then you can try these guys as well. But yeah, it's a little bit of a guess and check until you finally get it. I'm going to give you guys the answers for this one here, just because I'm nice today. So if you were to plug in 2/3 into that, it does give you a 0. Now let's check it out, see if it works here. Let's see. The 3 comes down, the negative 11 goes down, the 22 goes down. Ooh, hold on. Remember we're missing an x squared in here, right? So that means the x squared coefficient is a 0. Careful with those. And then 22 is the coefficient of x, and then the minus 12 all the way at the end. So bring down the 3. Ooh, this is fun. Multiplying by 2/3. Well, the 3's will cancel. Everybody okay with the 2 being over here? 2/3 times 3. Negative 11 plus 2 is a negative 9. And again, off to the side if you need to here, it's going to be 2/3 times a negative 9. Do that off to the side if you need to here. So the 3 is going to reduce down the negative 9 to a negative 3. And negative 3 times 2, how about a negative 6? Good there. 0, man, that'll be a minus 6 there. Alright, let's see what we got here. Let's see, 2/3 times negative 6. The 3 reduces the negative 6 down to a negative 2. Negative 2 times 2, negative 4. And that 22 minus 4 is an 18. And then again, going back over here, 2/3 times 18. 3 reduces down that to a 6. 6 times 2 is 12. Adding down, there's my 0. Cool. All right, can you rewrite like we did last time here? So I need an x minus 2/3, right? I need this guy here. I want to rewrite this guy in factored form. So x minus 2/3 comes down. And then this whole piece right here. So that means this is 3x. Let's see, that was to the 4th power. Now we got it to the 3rd power. We went down 1. So this has to be a minus 9x squared. How about a minus 6x? How about a plus 18? Equal to 0. So notice, even though it was a function, it told me to find all the real zeros. I just started equal to 0. Okay, if that's the case, let me rewrite it so we have it in front here. So because I need it for later on here, let me rewrite the whole thing here. Set equal to 0. Okay. So I know that 2/3 is the answer. So now let's deal with just this piece right here. So 3x cubed minus 9x squared minus 6x plus 18. Okay, you guys, a couple of choices here. You could maybe possibly check. Look at that, you got 4 terms here, right? factoring by grouping, remember that one? If you have 4 terms, possibly that might work. We good? We could just start factoring this. So let's factor out a 3. Again, whichever you like. You can just start P over Q already. The only suggestion is maybe not do P over Q when you can factor something out, because you want to have lower numbers, the better. So how about this? Let's factor out a 3. So how about 3x cubed minus 3x squared minus 2x plus 6. Divide both sides by 3. At least you don't have to deal with larger numbers here. Okay, this one I did not try factoring by grouping. I didn't personally. I started just P over Q again. Just see what we're gonna happen here. So P, possible factors of 6, plus or minus 1. How about plus or minus?
Wait, why are we doing this?
Ah, cool, because we haven't got down to x squared. Right, once you get down to x squared, that's when you can use quadratic formula, and you're done. Okay, Q. What do we get for Q? I like this one. I like when there's no coefficient in front of you. That's just going to have to be plus or minus 1. So possible values for P over Q. That looks weird here. Let me correct that here. Let me get to where we're at. P over Q is just the P values, just the way they were, because a divisor of 1 doesn't change anything. It's all yours here. Can you plug in some values? Tell me which one works. At least this is a lot better, right? Because when we started off this problem we had, let's see, let me count, 1, 2, 3, 4, 5, 6, 7, 8, 9. We had 18 different possibilities. Now we're down to 8 different possibilities. And again, anybody tell the group when you find it. You find the number as you plug it in would give you a 0. Cool. Okay, I heard a positive 3. You guys, someone else check it just to make sure. We'll check if 5 is correct or not. Are we good? Okay, I get a second on the 3. Yes, 3 works. As you plug in a 3, that makes 27. Looks like subtract 27, and then it makes a negative 6 plus 6, and yep, that should make us a 0. Cool. So let's go for it here. I want to see what is the remaining polynomial that's left. Sorry guys, yep, these problems are long, especially this one here. I gotta go. Keep on going all the way down. All right, of course, some stories, right? Has to be some stories as we finish up stuff. You know how we have a quadratic formula, right? It's for x squared, right? In the early 1600s, there was mathematicians. The name of the game in the early 1600s was, can we figure out a cubic formula? Can you figure out a formula that works for any cube whatsoever, like just like we use for the quadratic formula, right? So ax cubed plus bx squared plus cx plus d equals 0. For that. And so there's a person by the name of Tartaglia, mathematician. He figured it out. He figured out a cubic formula, a generalized cubic formula. Then, as soon as that was done, of course, then the question was, is there, and can we find a x to the fourth, a fourth degree general equation formula? And so, couldn't do it. No one could figure it out. And then there was a guy by the name of Galois. He figured out that he can prove mathematically that you can't have any general formula for x to the fifth power. There's no general formula for degree 5 or higher. And so eventually, almost about 150 years later, we finally got a general formula for x to the fourth. It's humongous. We don't use it. Quadratic formula is at least doable. So we don't have there is a general formula for x to the third power. So we could have actually plugged this into like almost like a quadratic formula and be done. That's kind of cool. I think so. Galois, as the story goes, gets into a fight with another guy at the bar. So he says, hey, it was a duel. So he says, I know I'm not going to win. So he writes down the formula that he's been thinking about in his head, which is the proof. Well, no, not a formula. He writes down the proof that there is no such thing as a generalized formula for x to the fifth. So he hands it to a math friend of his. He goes out. He dies at age 22. So that friend looks at it like, yeah, this is probably not something important. His scribbles again. He dumps it in a drawer. And so as the janitor comes by to start, mopping up things, and because he was a somewhat of a professor at that time, he says, as he's about to throw this in the trash, he says, just maybe this is of worth, So he takes the papers, instead of throwing them in the trash, he takes it and gives it to the resident mathematician on campus at the university. And so he starts looking at this. Says, no way, this is what we've been looking for. Anyways, to make a long story short, the mathematician tries to prove it and take credit for it himself. Like, that's kind of cool, right? The guy's dead, might as well take credit for it. Except he can't prove, as the proof goes, he can't figure out what Galois is doing this part of the proof, so he says, forget it, who cares, So he stuffs it in a drawer. 17 years later, as this person retires, another mathematician comes in to be the chair of the department. He picks it up and knows that part of the proof, what that's all about. He goes, this is awesome, and again gives credit to Galois for finding it. That's kind of cool. All that good stuff in mathematics. Okay, so enough waste of time here. Okay, let's go. Adding 1 down, 3 times 1 is a 3. Adding that down gives you a 0, and 3 times 0 is still a 0. Adding this down gives you a -2 times 3 gives you the -6, and there's your 0. Cool. Okay, got it. 3 is a solution. What's this polynomial that's left? Awesome. Okay, x squared minus 2. Let's solve that guy. Now we're down to x squared. So yes, we can use the quadratic formula if we need to. We can also, you can't, hold on though, real quick here. Can't factor it, right? Quadratic formula actually will take too long. What's the easier way to do this? It's called solving equations by perfect squares, or the square root method of solving an equation. You guys remember that one? You move the 2 over, so you get that, whatever that thing is being perfectly squared by itself. And again, you could do it by quadratic formula. I'm not saying you can't. Can't factor it, that's the only problem here. Well, can I say this real quick here? Yes, you can. You can factor this down. That's perfectly fine. We'll see a little bit later. But anyways, move the 2 over. How about this? Is that right? Take a square root of both sides. The only thing we've got to do is put the little plus or minus. And we get ourselves a plus or minus square root of 2. Okay, can you write for me all the zeros that we got so far? Or actually, no, all the zeros that we have. There's 4 of them. It's x to the 4th. That means we got all of them. Alright, hopefully we got it here. So x is equal to, remember 2/3 all the way in the beginning? Remember the 3 that we got a little bit later? And how about the plus or minus root 2? There's my 4 zeros. That's kind of cool because I got them all. Okay, what is this all leading up to? It's leading to the fact that we can finally make a graph. A rough graph, but it's still a graph of our function. And so we'll do this a lot more later on, but let's do it. Let's graph this. The next problem here, because that's all we're leading up to. Here's what we want to be able to do. We want to be able to look at this function, do a little bit of math, and graph it. In your book, it does give you like a 5-step process to do this. Step 1 is talking about end behavior. See if we can remember this from Tuesday's class. What do you guys say? This is an x cubed polynomial with a positive 3 as our leading coefficient. What do you guys say? Start high, start low, end low, what? So off to the side, you should sort of have this in your mind, right? X cubed looks like this, right? With a positive 3 in front, it just means it looks more skinnier. But notice what we want is in behavior. We want to know that it starts low, ends high. X squared would, let's see, x squared would start high, end high, right? With the leading positive coefficient. Okay, so what's this? Step 1 for this process is called EB, or we call it end behavior. End behavior is what we're looking for. Let me find you the 5-step process here so we got it. The 5-step process, if you want to follow along. It's on page 342, 343, and they really just give you an example as you follow along. But let's go for it here. So in behavior, everybody agreed? It starts low, and it's going to end high eventually. Next thing is to figure out all our zeros. All right, the y-intercept is the easiest to get. What is the y-intercept? No, absolutely. If this is a 0, that's a 0, that's a 0, I got a y-intercept of 3 right away. X-intercept, that's the fun part. That's what we got to figure out. So here it is. That is when we have to do this. We got to set all this guy equal to a 0. I think we got to do P over Q, right? P is all the possible factors of 3. Q, hey, that's the same thing. It's all the possible factors of 3 because there's 3 in the front, 3 in the back. All right, P over Q. You guys list them for me. What are they? Plus or minus 1, I heard. Yep. And I would probably do this here. We'll go 1 divided by 1. 3 divided by 1 is a 3. So all the different possibilities of combination with P of Q being 1. And then we go 1 divided by 3 here is a 1/3, and then 3 divided by 3 gives you that 1 again. Alright, here we go again. Guessing and checking, plugging it in, see what happens. Should I be kind to you again and see and tell you which one it is? How about this? I'll try, because of the little 3 in front over here, what I would probably try, I would try a 1/3 or a negative 1/3. Try either of those. Let's see what you guys get. Let's see. Anybody? Negative 1/3 or positive 1/3? What do you guys say? Positive 1/3? Perfect. Okay. Coefficient of x cubed, coefficient of x squared, coefficient of x, and constant coefficient 1/3 I think should work. I'll let you guys finish that off using the synthetic division. Okay, 3 goes down. Let's see. 1/3 of 3 is just a 1. Negative 1 plus 1 is a 0, and 1/3 of 0 is still a 0. Negative 9 plus 0 is a negative 9, and 1/3 of a negative 9 is a negative 3, and voila, there's my 0. Polynomial that remains.
I forgot what you were looking for. Thank you.
Polynomial that's left over. Are we okay with 3x squared minus 9 is equal to 0? Alright, now I'm going to solve this guy. But we're down to x squared now, so that's good. So let's go for it here. So 3x squared minus 9 is equal to 0. Again, I'll probably factor first. Get the 3 out of the way. Divide by 3, you get yourself a x squared minus 3 equals 0. Good there so far? You could have actually just added 9 divided by 3. Either or, you eventually wind up with something that looks like this. Is that good? Square root both sides, plus or minus, don't forget that. So I got x is equal to plus or minus root 3. So there's my square root method of solving a quadratic equation. Okay, all my zeros. Let's go for all my x-intercepts, I should say. All my x-intercepts are 1/3. And I got plus or minus root 3. Okay, once I have that in place, and again, the important stuff, really the important stuff here is in behavior and intercepts. If you can get that, you got yourself at least a rough graph. So let's go for in behavior for this guy. Actually, let's put our zeros down. 1/3 is going to be about right here. 1/3 of the way from 0 to 1. Anybody, real quick here, what's the square root of 3? Approximation for root 3. 1.73, okay. So I got a positive 1.73, I got a negative 1.73. So I got a negative 1.73 is about right here, a little bit past negative 2. And then how about right before positive 2? All right, let's see. The other thing is, I got my zeros. Y-intercept. There you go. Y-intercept. Well, I almost forgot. That's a 3, right? All right, let's see if this works here. In behavior, remember it starts low, ends high. And so now the question is, can you connect all those? I think so, huh? Start low, and we're going to work our way up here. So we're going to work right to the 0, cross the 0, go up. Looks like it's going to go up first, and then starts coming back down because the other 0 is so close. It's going to come down past that 0, and then starts turning back around to get to that 1.73, and then eventually wind up, hey, meeting that arrow at the end. We good? Again, we'll practice a lot more with these in 3.6. That's when we'll be doing quite a bit of graphing there. Okay, but again, in behavior and intercepts. Once you got those, you at least have a pretty good estimation where you're at. Okay, got 45 minutes left here. All right, now what we want to deal with is we want to deal with all possible zeros. So really what we're doing, we're including the complex zeros now. So think about square root of a negative number, because we haven't had that yet. And what does that give us because of that? So we're going to learn, again, real quick here, some basic facts of complex numbers or complex zeros, and then something called the conjugate pairs theorem. Whenever you deal with complex numbers, they always come in pairs. So if you have a positive root 3 as a answer, you know you got a negative root 3. Or a 1 plus I, 1 minus I. You're going to always have those. Okay, but let's go for it here. Okay, a few things to note. First of all, don't need to write this down, but every polynomial function, all the way from x to the nth power, all the way, if you write the polynomial all the way down to the constant coefficient, will have, and this is kind of what's important here, will have the same number of complex 0 as the number of the degree. Okay, so if you count all the real zeros and you count all the complex zeros, count how many zeros you have, they shall always get to the point of adding up to the degree that you have. Good. So what we can do is we can write a polynomial. We can write it just in terms of zeros all the way through. So if you include the complex zeros, you can always factor it all the way down. That's kind of what we're looking at. Okay, now the only thing is, a little caveat here for me, is that they're not always necessarily distinct. So remember, if you were to factor down x squared minus 4, right, something looks like this. Right? Your factored form would look x minus 2 and another, this would be x plus 2. We're good there? Those two are distinct, right? X minus 2, x plus 2, they're not the same. But if you had something looks like this, let me write it on this side here. So you got x minus 2 squared, right? And there's 2 of those, right? So you can have some repeating. If you're looking at complex numbers, you can have some repeating ones, but again, you can always count the number of zeros you have, figure out what degree you have, and you can figure out whether you got all of them at the end. Okay, let's go for it. First things first, we got to be able to expand, so we're going to go sort of backwards first. And I got 4 problems on my hands, but they are long. So we got 4 problems, but we're going to take a long time to get them done here. So find a polynomial. We're going to go backwards here. If you know what the zeros are, the zeros are negative 2, a 1, 1 plus I, 1 minus I. I want you to write the polynomial that makes that true. The other thing that we know is it's a degree 4. And the next thing that we know is the fact that the leading term is 3. Or the leading coefficient is 3. Alright. Put on your thinking caps here for a little bit here. This will be interesting ride here. So here's what we want to do. We want to be able to write it in terms of A. In terms of A, we want to write a polynomial that looks like this. A on the outside, that's my leading term. It's going to be x minus r1, x minus r2, x minus r3, and x minus r4. The reason why I stop at 4, because we have a degree 4 on our hands. Okay, let's fill in everything we know. So, p of x is equal to, what's my leading term? Or leading coefficient, I should say, sorry. It's a 3 right here. We got that taken care of. So now we go with, let's see, if I know my 0 is a negative 2, what's my factor? X plus 2, good there. That's always going to be the exact opposite. Again, if you set x plus 2 equals to 0, you're going to get x equals negative 2 is the answer. So kind of working backwards here. Okay, if I know that 1 is my root, what's my factored form then?
What was the question?
Sure. If I know that 1 right here, 1 is a solution, what's the factor? Well, okay, I got it. X minus 1. Perfect. Thank you. All right, here's the tough part now. If I know that 1 plus I, bless you, is a solution, bless you, what's my factor? It's x minus, in parentheses, 1 plus I. Oof. Good there? It's the subtraction of this piece here. Just like it's right over here. This would be x plus 2. You can also write as x subtract a negative 2. Because 1 is a factor, we could have wrote it as x minus one, which is the way we wrote it. Okay, got it. Sorry. Just kidding. Okay, next one. Since we know that 1 minus I is a solution, we've got x subtract 1 minus I as a factor.
Wait, why did you write it like that?
Mm-hmm. Question is, why do we write it like this? And I think the algebra textbook that we use probably gave a little better illustration here. If you know that x is equal to negative 2, what we do? No, we'll get there yet. There's my factor. There's my multiply that gets me the 0. We good? Same thing here. X is equal to 1. If we subtract 1 from both sides, gets me this. There's my factor. If I know that x is equal to 1 plus I, what we do is we subtract out this on both sides. Kind of looks funny at first, but that canceled, and that gave me the 0 that I want. This book, what it does is it gets it directly into factored form right away. So it says, okay, what we're going to do here is we're just going to subtract. This should have been x minus a negative 2, because then what we do is we just do this. This, since 1 is a factor, it's going to be x minus 1, and that's what we got. Since x minus 1 is a factor, it's x minus and whatever this factor is. All right, let's get rid of these extra parentheses here so we don't have to have them. Okay, we're good there with that one? All right, let's see what we've got here. 3 on the outside, x plus 2. We've got x minus 1, but let's get rid of this extra stuff. So x, distribute the negative, makes minus 1 minus I. This will be x minus 1 plus I. All right, here we go. We're gonna multiply all this out right here. So let me rewrite it on the next slide, just the way we had it. So can you, real quick here, multiply x plus 2 times x minus 1? Can you multiply this part? Hole in your head here. 3 is on the outside. X plus 2 times x minus 1. I go with that here. Let's see, x squared. Let's see, plus x minus 2. Everybody good there? As you multiply in here, that's going to be negative x plus 2x makes the positive x, and 2 times negative 1 is negative 2. Okay, the fun part is this one right here. I got to FOIL this out. Okay, one little thing here. When you FOIL this out, all the I values better cancel or else you did something wrong. Cool, so off to the side here, I'm going to do it with you guys here. X minus 1 minus I times x minus 1 plus I. So let's see, x times x. X squared. X times a negative 1. X times I. So xi. Got the first term taken care of. The negative 1, let's multiply the negative 1. Negative 1 times x is negative x. Negative 1 times negative 1 is a positive 1. Negative 1 times I is a negative I. Okay, last term. So negative I times x, this guy here, that's going to give you negative xi. Negative I times a negative 1, so plus I. Okay, the fun one here, negative I times a positive I. Let's see, off to the side maybe. Negative I squared, is that right? Negative times a positive is a negative. I times I is I squared. What is I squared again? Negative 1, so that means technically it's a negative 1, or just plus 1. Cool, cancel anything that is like terms. Let's see, I got an xi, cancels with a negative xi. I got a negative I with a positive I. So my end result is, how about x squared? I got minus 2x, is that right? Got an x here and the x here. And then plus 2 looks like, because I got a positive 1 plus another positive 1. Okay, let me rewrite this because I'm running out of room here. So that form now. Everybody good there? Okay, 2 more steps here. Now you get to FOIL this out for me. So what is the trinomial times another trinomial going to give us? I'm going to write it as well here. Let's see. So 3 on the outside, but this is x times x is x to the 4th. X squared times negative 2x, so it makes negative 2x cubed. X cubed times 2 makes positive 2x squared. Everybody good there so far? What I like to do, instead of writing it all horizontally and trying to find the like terms, this is just me, I would rather multiply these guys together. So x times x squared makes x cubed. I'm going to write it underneath the like term itself, so I can just sort of add them up a little bit later. Makes it a little bit easier. I think I mentioned that to you guys before here. So x times negative 2x is negative 2x squared. X times 2 is 2x. Multiplying by 2 everywhere. Negative 2 times x squared is a negative 2x squared. Negative 2 times negative 2x, positive 4x. And negative 2 times a positive 2 is a negative 4. Adding that up together, so 3 on the outside, x to the fourth. How about a minus x cubed? How about a minus 2x squared plus 6x minus 4? Good there so far. One final step. Let's distribute that 3 finally. So I'll write down the final answer. Whew. Okay, we sort of did it a backwards way. I gave you the zeros already. So this polynomial would factor down and give us zeros of negative 2, of 1, 1 plus I, 1 minus I. Long process here. Okay, I've got to do a theorem here, and then we'll do it the forwards way. One theorem that comes out of this, and it comes out of the quadratic formula, is the fact that if you know you have a I as an answer, you know you also have a negative I as an answer. They always come out in pairs here. So it's called the conjugate pairs theorem. Let me give you page number so at least know it, and then that'd be it's on page 349. And it really comes from the quadratic formula if you think about it. If you have something that looks like this, let's say it's like 4 plus or minus 3 root 5. 2 root 5 over 2. We'll put a little negative right here. Notice what's going to happen. Because it's a little plus or minus right here, you're going to get yourself a 2 plus or minus I root 5. Are we good there? So notice you're always going to have, if you have a 2 plus I root 5, you're also going to have the 2 minus I root 5 because of the quadratic formula. So that's what this says. If you see a plus bi as a 0, you know automatically there's also a minus bi also as a solution. So let's just work with that just for a little bit here. So practice problem number 2. We have a degree 8 polynomial. How about that for some? And then we come back to this multiplicity thing that we talked about in 3.2, or else you read in 3.2 if you read it. No, this is just write for me all the zeros of p of x. Can you give all the rest of them, or can you give me all of them? So let's go. And this is really just an exercise with the conjugate pairs theorem. So whenever you see a complex answer, you know that its pair is also there. And then this whole concept of multiplicity. Remember, multiplicity says that's how many of the same factors I have, or the same solutions I have. So we got to get to 8. Somehow it has to have 8 because we have the real solutions as well as the complex solution. We've got both of them. So if we have both of them, it has to reach up to 8. So let's go for it. If you know that negative 3 is an answer, that's good. And then it also has each with the multiplicity of 2. If that's the case, then you also know you got another negative 3 as an answer. Good there? Okay, then it says you have 2 minus 3i as a solution. And it has multiplicity 2, so therefore you have another 2 minus 3i. Okay, now the question is, what two other roots do you know automatically? You know you have 2 plus 3i, and then another 2 plus 3i automatically. Good there, because of the whole concept of the conjugate pairs. Okay, and then also you have I as an answer. It's given to you. So then what else do you know to be a root? So I shouldn't say root, I should say 0. Whatever the conjugate of I is, right? In this case, it'll be negative I. Okay, we're good there?
Why do you have two negatives?
Because it says multiplicity 2 right here. Okay, I think we're ready to do it from beginning to end here. Let me just see so we don't get too confused here. Yeah, hope it takes that long here. Okay, so let's do it this way here. Let's look at an example first of all, and then you guys will try one yourself here. So first of all, the example. So we're trying to find all the complex zeros of this polynomial. We're trying to factor this down completely. It is a degree 4 polynomial. There it is. Humongous monster here. This one could contain complex answers as well as real answers. And also it even tells us that 2 minus I is actually a 0 of this guy right here. We figured that out already. So here's what we're going to do. We're going to take this 2 minus I concept and we're going to plug it into a factored form right here. So x minus 2 minus I, and then you got x minus 2 plus I. Good there? I think we did this already. We got rid of the inside parentheses. We multiplied everything out. In fact, there's a little easier way to do it. Let's do the easier way. Notice you have an x minus 2 here, plus I. You got an x minus 2 minus I. Aren't those actually two perfect squares? So if you multiply this out, what's that going to give it? Isn't that x squared minus 4x plus 4? Maybe?
Yeah.
Right, so this guy's going to be off to the side here. X squared minus 4x plus 4. And then you got this whole concept of negative I squared. We talked about that one as well. What's that going to give us?
1.
Yeah, plus 1. So adding this up together eventually gives you that right there. Good. X squared minus 4x plus 4 plus 5. Does that factor? Just real quick out of curiosity. Can you factor that down real quick here in your mind?
Yes. X plus 5 and x. Oh no, x minus 5. And, nope, never mind. No, it can't.
If the signs were switched, yes, you can, right? But not this way. Not with the signs being a negative 4x and a positive 5. So that's why it's going to be a complex answer. Okay, you know that because we start off with the complex answer. Okay, since you know 2 minus I is a complex answer, you know 2 plus I is also an answer. You multiplied it all out, you got yourself a trinomial here. What are we going to do with this? Don't we know that this guy is a factor of this whole thing? So here's what it looks like. Hey, long division again, look at that. We're going to divide what we formed into x to the 4th polynomial. As we do all that division, it better be a 0 here, right? Because we're saying that it is a factor. The leftover stuff here, can we factor this guy down? Anybody? Need two numbers, multiply to 1, add to -2. I go with that. X minus 1, x minus 1. Doesn't that factor down there? So then, breaking everything down, x squared minus 4x plus 5 breaks down into this eventually. X squared minus 2x plus 1 breaks down into this. What are my zeros? I have a 1, which has a multiplicity of 2, right? There's 2 of them. And then I have 2 minus I, 2 plus I. So there's my 4 zeros. Started off with x to the 4th. Counting multiplicities, I wind up with 4 zeros. And then I know I'm done. There's no other zeros left to find. 2 problems. Probably take us about 10 minutes here. So let's go for it. Let's try it ourselves here. Give you guys a head start. All right, so we'll go for it. Given that 2i is a 0, got a few things here in our hands. Don't we automatically assume this is a factored form? Also, don't we assume that x plus 2i is also a factored form? Cool, let's multiply that out, see what we get. In this case, x times x is x squared. X times 2i makes a positive 2i. Negative 2i times x gives you negative 2i, or 2xi. Okay, the fun one here it is. Negative 2i times a positive 2i. Perfect, yep. You get a negative 4i squared. Since I squared is a negative 1 already, we get ourselves just a plus 4. The middle terms cancel and got myself this. So there's my polynomial that's created because of my complex roots, or complex zeros. Okay, I'm going to use that, x squared plus 4, and I'm going to divide into this humongous 4th degree polynomial. All right, and notice what it says here. It says find the remaining zeros. All right, let's go for it here. Let's see. What number times x squared gives you 4x to the 4th? That'd be x squared. X squared times that gives you x to the 4th. 4 times x squared gives you a positive 4x squared. And we subtract everything out. All right, x to the 4ths are canceled. But we do have to bring down the leading coefficient, so don't forget you got to bring down a negative 3x cubed. All right, then we go 1 over from there. Alright, so let's go with, let's see, what multiplies x squared to give you negative 3x cubed? That should be a minus 3x. Multiplying that times x squared gives you a negative 3x cubed. Negative x squared times a 4 gives you a minus 12x. And again, we subtract everything out. In this case, kind of funny, those would cancel if we're subtracting. And we have no x to the 1 term anymore because the coefficient is 0. Alright, and what number times x squared gives you 2x squared? Positive 2. And if we do that, again what happens is those will cancel as well. Remainder is 0. So awesome. So let's see how this went here. Let's see. First of all, we start off with x to the 4th and all this stuff here. Now that we know x squared plus 4 is a factor, we also know that x squared minus 3x plus 2 is a factor. So rewriting this in factored form, I'd write it like this. Everybody good there? Yep, and I'm going to check something just real quickly here. All right, look at this here. Can I break down this one some more? I need two numbers multiplied to 2 add to negative 3. I think so, is that right? X equals negative 1 and x minus 2. Awesome, okay, so give me the remaining zeros. So one of them I know to be a 2i, a 1 and a 2. And the only thing we should know, because we were only given a positive 2i as an answer, right? The other one's that one, right? We knew that from the beginning just because we knew that positive 2i was also a factor. Okay, so really we come down finally to the last one here. This sort of puts everything together. We want to start off with x to the fourth polynomial, and I want you guys to find all the zeros, both complex and real. So from beginning to end, you should be able to find 4 of them. They may repeat themselves, but you should be able to find 4 of them. We're going to use the P over Q stuff as well. And we're running a little bit at a time. So I'm going to start it, give you some hints along the way, give you guys a minute maybe to try to be a little bit ahead of me. So starting here, let's go with P over Q. So P would be all the factors of 16. There's somewhat quite a bit of them here. How about plus or minus 1, plus or minus 2, plus or minus 4, right, because 4 times 4 is 16, plus or minus 8, and plus or minus 16. Okay, what's a few other things here that we got? Q. Oh, Q, I like Q. Q is just going to be plus or minus 1, because that's there's only 1 in front of x to the fourth. So P over Q, it's just going to be all the factors of P, just like we had before, because if you divide out by 1, you just get the same thing anyways. Alright, anybody got an answer that worked? 2 works? Cool, okay. Cool, I heard a 4. Okay, I got the 4 when I did it. So 1, negative 8, 22, negative 28, and 16. I'm going to use a 4. So 1 goes down. 4 times 1 is a 4. Negative 8 plus 4 is a negative 4. 4 times negative 4 is a negative 16. Adding down, you get a 6 left over. Is that right? Yep. 4 times 6 is 24. Alright, adding down gets you negative 4. Negative 4 times 4 is negative 16. Perfect. There it is. Okay, write for me the polynomial that is left, if you haven't done so already. We start off x to the fourth. So we're going to go down to x to the third, right? So this has to be the coefficient of x to the third here. So writing this guy, this should be 1x to the third, or just x to the third. Negative 4 has to be the coefficient of x squared. 6 has to be the coefficient of x, and minus 4 is the constant coefficient. Almost there. Hanging tight here. Almost there. That's the polynomial that's left. Let's set that guy equal to 0. So x cubed minus 4x squared plus 6x minus 4 is equal to 0. Alright, what should we do here? We're going to do P over Q again, because we've got to get it down to x squared here. So P over Q, or P, it would be plus or minus 1, 2, and 4. And then I heard someone say 2 worked, right, for them earlier. So let's try 2. Q again is a 1. So P over Q is really just the same thing as Q. Okay, good. Miles, good. So 1, -4, 6, -4. And we heard that 2 works. Go for it. So bring down the 1. 1 times 2 is 2. -4 plus 2 is a -2. 2 times -2 is a -4. Bring that down, gets you a +2 this time. And 2 times 2 is 4. Voila. Awesome. Alright, polynomial that's left. X squared minus 2x plus 2. And the question to you guys, does that factor? Shaking their head no, so I sort of agree with that. It's a no, so let's go with quadratic formula at this point. You guys a head start on the quadratic formula, maybe 15, 20 seconds worth or so. I'm going to write down the answer here, just sort of look up when you are done, or look up if you're stuck. Simplifying this out gets you a -4 inside the radical. And because of that, eventually should get a 1 plus or minus I. Alright, then solving it, listing all the zeros that we found so far. We found 4, we found 2, and we found 1 plus or minus I. We found it, started with a degree 4 polynomial. We got our 4 zeros, right? We know that is it. There are no more. Okay, why is this so important in calculus? The name of the game would be to find your zeros. That's a lot, especially after you take a derivative. You want to find those zeros that happen. And so this is, in a sense, all the tools we have. You learned quadratic formula probably in Math 63 or elementary algebra. You got to use it a little bit better. Let's see what else we got. We got the square root method for solving an equation. If you go on the internet, you can find the generalized cubic formula. That'd be kind of fun. You can use that. But other than that, we just have P over Q. That's it. So usually what we do is we do P over Q, break it all the way down until you get x squared, and factor quadratic formula. So we've sort of got to the end of how we solve polynomials, which is kind of cool. Other thing that we have for polynomials, we could always graph it using a graphing calculator, and then use some kind of calculating technique that the calculator uses to find the zero. That's the only other way that we could do it, but that's kind of cool. We come to the end of polynomials as we know it algebraically. Okay, with that I stop.